And our next speaker is Peter Steigenberger from DLR. So Dr. Peter Steigenberger is a senior researcher in the GNSS technology and the navigation group at the DLR's German Space Operations Center. His research interests focus on GNSS precise orbit and clock discrimination. Please join me to welcome Dr. Peter Steigenberger. Peter, time is yours.
Thank you, Zhang-Hui. Yeah, so now you can hear me. So thank you, Zhang-Hui. My presentation is focused on the orbits and clocks F BeiDou 3 provided by the MGEX analysis centers of the IGS Multi-GNSS pilot project. And my co-authors are representatives of these analysis centers contributing their products to MGEX. So let me start with a short overview about the current BeiDou constellation. We have 15 satellites of the regional BeiDou 2 system, 3 of them in medium Earth orbit, shown here in pink, 7 in inclined geosynchronous orbit in blue, and 5 geostationary satellites. After the BeiDou 2 system, there was a test system, let's say, of currently 5 active satellites, the BDS 3S system. None of these satellites is currently set healthy, and none of these satellites is processed by the MGEX ACs. And as the global system, we have BeiDou 3 with 24 medium Earth orbit satellites in 3 orbital planes, 3 IGSO satellites, and 3 geostationary satellites. 2 of these are healthy, and 1 is currently in the stage of testing. So let's have a look at the backbone of the current BeiDou 3 constellation, the medium Earth orbit satellites. There are 2 different types of satellites from 2 different manufacturers, from the China Academy of Space Technology, abbreviated CAST, and the second one from the Shanghai Engineering Center for Microsatellites, abbreviated SECM. And if you have a look at the body of these satellites, they have a different shape. So the CAST satellites have a elongated body, and the second satellites have a stretched body like the Galileo satellites. And this, of course, has some impact on the orbit modeling. The rough geometrical dimensions, as well as a limited set of optical properties of these 2 types of satellites, was provided already a few years ago by the Chinese Satellite Navigation Office, and this metadata allows to construct a box wing model, which is used by some of the analysis centers. The IGSO and GEO satellite have a much more complex shape. So they have additional quite large communication antennas, and the dimensions as well as the optical properties of these antennas are not known. And as a consequence, they are neglected in the orbit modeling and introduce dedicated errors in the orbits of these types of satellites. In the multi-GNSS pilot projects, the successor of the multi-GNSS experiment, abbreviated MGEX, we have currently 7 analysis centers, and 5 of them provide BeiDou products, BeiDou 2 as well as BeiDou 3. But as you can see here in this table, not all analysis centers contribute all types of orbits, so the geosatellites are not processed by all of the analysis centers. We have in general 2 types of products: final products with a higher latency. For example, Code also submits them in weekly batches. And we have the rapid products with a lower latency. Please let me add that, for example, Wuhan University in addition provides ultra-rapid products with an even higher update rate, but in this analysis here, only the final products of Wuhan University are considered. In this slide, you see a very few selected modeling options. So there's a quite large variety of options. I put here only a few of them to show you which options differ in particular between analysis centers. So the arc length varies between 1 day and 3 days. Some analysis centers apply an a priori model, the a priori box wing model, but different types of models. As I mentioned, the optical properties are not complete that are published, so these have to be supplemented somehow. The estimated solar radiation pressure parameters are also different. Code, for example, uses the ECOM2 model. Most of the other analysis centers, the 5-parameter ECOM model, and ISC uses a special subtype of ECOM model where the parameterization depends on the elevation of the sun above the orbital plane, so the beta angle, and depending on this angle, different types of parameters are estimated. Considering the albedo and infrared radiation of the Earth, the acceleration of this radiation on the satellite is quite a standard for GPS. So all analysis centers contributing to IGS Repro 3 considered this effect for GPS. But Tom already mentioned this, due to lack of data, this effect is currently only considered by 2 analysis centers, and we will later see how these impacts the results. So let's now come to the consistency of the orbit products, and the measure I used here is the orbit signal in space range error, abbreviated orbit SISRE, and this orbit SISRE is computed always between a pair of analysis centers and from the RMS orbit differences in the radial, along track, and cross track directions. These are multiplied with weighting factors that depend on the orbit height. On the right-hand side, you can see the different orbit SISRE values for pairs of analysis centers. So for the medium Earth orbit satellites, they vary between about 4 and 7 centimeters. And for the IGSO satellites, from roughly 10 to 25 centimeters. So this is related to the more complex shape of these satellites, but also to the regional character of these orbits. So the number of stations tracking these satellites is significantly smaller than for the MEO satellites. The geostationary satellites are not shown in this plot because they exceed this range that is shown here. They have orbit SISRE values on the level of 50 to 60 centimeters. The orbit SISRE was a measure for the internal consistency, and the satellite laser ranging can be used to evaluate the accuracy of the radial component of the orbits. All satellites of the BeiDou system are equipped with SLR retroreflectors. Unfortunately, only 4 satellites of the BeiDou 3 constellation are tracked by the ILRS. These are 2 MEOs of the CAST and 2 of the SECM type. And if you have a look at these box whisker plots of the residuals, you can immediately see a difference for all analysis centers between these 2 types of satellites. So there's a significant difference in the bias of the satellites. So all analysis centers show a positive bias for the CAST and all a negative one for the SECM satellites. But there are also differences between the individual analysis centers for one satellite, and these are attributed to modeling options affecting the radial component, namely albedo, infrared radiation, but also antenna thrust, and in general, the solar radiation pressure modeling. Overall, we can see here standard deviations in the range of 3 to 5 centimeters, and the RMS values are between 3 and 9 centimeters. Let's now have a look at the clocks. BeiDou 3 satellites are equipped with passive hydrogen masers, as you can see in the picture on the left-hand side, and rubidium clocks. And one example for a pretty good performing rubidium clock is shown on the right-hand side, the median Allen deviation of a CAST MEO satellite for the 5 different MGEX analysis centers. You can see here a pretty flat Allen deviation, so only smaller bumps at higher integration times for a few analysis centers. As I mentioned, this is a pretty good performing clock. There are also some other medium Earth orbit satellites that show bumps in the Allen deviation at higher integration times. For the IGSO and GEO satellites, the situation is a little bit worse. I have to mention that the physical clock is identical on these types of satellites. So what you see here is the apparent clock as determined by the GNSS observations. And this is slightly worse for the IGSO satellites. So you can see here a flattening at higher integration times. And this is related to orbit modeling deficiencies. You have seen that the orbit performance is worse for this type of satellites, but the consistency of the analysis centers is, again, pretty good. For the geostationary satellite, all three analysis centers that process this type of orbit show a pretty pronounced bump at about 10 to 20,000 seconds. And this is related to the even worse orbit quality of the GEO satellites. And this is related to the stationary geometry, resulting in correlations between the satellite clocks and, for example, ambiguities and station heights. And therefore, we see there a pretty bad apparent clock behavior at longer integration times. Let's now have a look at the overall constellation clock performance. So we have here median clock RMS values determined with respect to a second order polynomial, a daily polynomial. And you can see in yellow the satellites that are equipped with a rubidium frequency standard, and in green the ones with a passive hydrogen maser. In general, there are the differences between each group of clocks is even higher than the differences between the types of clocks. So, for example, for Galileo, we see a pronounced difference between the rubidium and the hydrogen masers. This is not the case for the BeiDou 3 clocks. The IGSO and geostationary satellites are, again, worse, as we have already seen in the Allen deviations. So we can now put orbits and clocks together and have a look at a quality measure that uses both, namely the overall signal in space range error. So now also the clock differences enter this equation. And if you remember the orbit Zisser values that were slightly higher than the Zisser values you can see. So we are now at the level of 3 to 7 centimeters for the MEO satellites and about 8 to 20 centimeters for the IGSO satellites. And this is related to a compensation of orbit-related errors by the estimated clock parameters. For the geostationary satellite, this effect is almost not visible. So the overall Zisser for the GEOs is also on a level of 50 to 60 centimeters. Another method to evaluate orbits and clocks together is the performance of a precise point positioning. So I computed PPP solutions with the MEO satellites of BeiDou 3 for 1 month, 30 stations, daily coordinates, and the 1 sigma repeatability or the standard deviation of these solutions is shown here for each station and each analysis center. And if we form an average per analysis center, we are on the level of 2 to 4 millimeters for the north component. The east component is worse, as this is an ambiguity float solution. So no ambiguities were fixed to integers here. And we end up with an overall 3D performance on the level of 7 to 13 millimeters. So let me summarize. We have altogether 5 IGS analysis centers that provide BeiDou orbit and clock products in the frame of the IGS Multi-GNSS pilot project. The processing options are not as homogeneous as for other constellations, as in particular GPS, resulting in a slightly degraded consistency of these products. Nevertheless, for the MEO satellites, we have a consistency on the 4 to 8 centimeter level, and the SLR residual RMS is pretty the same. For a better characterization of the orbits and of the orbit performance, extended coverage of the SLR tracking would be encouraged. Unfortunately, there was essentially no progress since the last IGS workshop on this topic. The solar radiation pressure modeling is challenging. We have also on the MEO satellites some structures that cause shading, but in particular the IGSO and GEO satellites have these huge communication antennas that are not considered at the moment. They are not considered as no metadata is available, so the orbit quality could be improved if more detailed metadata is provided, but nevertheless, BeiDou 3 is a fully operational GNSS and it can contribute valuable to the geodesy and precise positioning application. That's all. Thanks for your attention.
Thank you, Peter. It's a very nice talk. So any questions for Peter? You can type here. Hi, Peter, you have a question in the chat box.
Yes, so the question is, are there ongoing work of generating BeiDou observable specific bias OSB products? There are, so Shanghai Observatory and also DLR provide DCB products. And I know that Wuhan University is also providing bias products, but there was no effort in recent times to combine them like this is done, for example, in the framework in the Repro 3 context.
Any more questions? I think we still have time to have some questions for Peter. Hey, Peter, I have a question for you. So from your summary, you said the processing options not as homogeneous as for other constellations. So do you have any thoughts on how we should coordinate the efforts from the world to improve the BDS processing strategies? For example, to make them more homogeneous and to keep some more progress, to take some more progress towards some an improved BDS orbit and clock?
That's a quite tricky question. So I think one issue is the missing metadata. So if metadata is missing, then some people do best guess estimates, some people do neglect an effect. So for example, we have some measured transmit power values, but these are based on assumptions for the gain pattern. Some analysis centers use these, some others use other best guess values, some analysis centers neglect this effect. So I think, let's say from the IGS view, the most convenient and best way would be to have official metadata for these effects.
Okay. You have a small question from the chat box?
Yes. Another question on the chat is on real-time QZSS clock and orbit products. I know that from the real-time working group, there are QZSS orbiting clock products, but the MGEX project only focuses on post-process products. So there's another question on now very often BeiDou is combined with GPS and multi-GNSS processing. Do you have any plans on generating independent inter-system bias products? To be honest, no. There's a question on the classification of the clocks shown on page 11. It is true that there are different clocks on board the satellites, and there is a status website from CSNO where only the current clock is provided. And the classification shown on this page 11 is based on the current status of November 2021. I do not understand the next question, to be honest. How was the PPP done, absolute or relative? In my understanding, PPP is always an absolute. positioning.
Yeah. Okay. If we don't have any more questions, so thank you, Peter. Thank you for your talk.
Thank you.
And we have to move on to our next speaker. So